Now we're going to discuss a third method, although the third method is really just an extension over the second one. But as way of motivation, let's start with a number. So we're looking at groups of order 396, which factors is 2 squared times 3 squared times 11. So first we note method 1. The counting elements method doesn't work so well for this because we have two different primes with higher powers. So I don't see any easy modification that would allow us to solve this problem. But let's look at the CELO conditions. So n2 is going to just be, n sub 2 has to be an odd number. You're going to get 1, 3, 9, 11, 33, or 99. That's a lot of choices. N sub 3 is going to either be 1, 4, or 22, because that's be congruent to 1 mod 3, and it has to divide 44. Finally, N sub 11 is going to either be 1 or 12. So method 1 doesn't work. If we try method 2, what is the smallest k such that this divides k factorial? Well, the smallest k is given by k equals 11. So that means we can rule out all NP values that are smaller than 11. Unfortunately, we didn't completely remove a list, so we didn't get to a contradiction yet. And we've still got lots left over here on these three. And so we're going to focus on one of these cases. 12 is a smaller number, so that's the one we're going to work with. And so the idea behind method 3 is permutation representations. So the previous one used this permutation action to get some sort of numerical condition. Now the idea is that you're actually going to take the permutation representation one step further and actually calculate with it and see if you can't get other contradictions. So in our case, G is going to act on the CELO 11 subgroups. So K is actually 12. So what does this 12 represent? It's also the index NG of the normalizer NG of any CELO 12 subgroup. CELO 11 subgroup. So fix your favorite one. What does that tell you about the order of G, the normalizer? Well, then it's going to have to be the difference, so it's got to be 3 times 11, which is 33. On the other hand, the normalizer of P and G is a subgroup of the normalizer in S12 of P. Or I should say phi of P, right? So we're identifying G as a subgroup of S12. So there's a divisibility criterion here, and the hope is to get a contradiction. And the contradiction would be that somehow there's a prime factor here that's not a prime factor here. So let's see if we can't calculate the size of this normalizer by calculating the size of this index. So what is the order of phi of P? Well, P has order 11. Phi of P also has order 11. This is a CeLO 11 subgroup. In S12. So in particular, this number is N11 for S12. So it's the number of CeLO 11 subgroups. But we're working with the permutation. We're working with the full symmetric group now. What is a CeLO 11 subgroup? It's an 11 cycle. Or, well, it's generated by 11 cycles. So you can take the number of 11 cycles and you can divide out by 10 to account for the fact that in any corresponding group, there's going to be 10 different 11 cycles in the same group. And so how many 11 cycles are there in S12? Well, you take some element to not put on the cycle, and then there's always n minus 1 factorial cycles in Sn. Divide by 10. We have 12 times 9 factorial. Well, that puts the size of this subgroup at 11 times 10. It's 110. So what do we have? We've got the normalizer of G of P is a subgroup with a normalizer in S12 of P. So by Lagrange's theorem, we should have 33 divides 110. Oops, that's a contradiction. So it must be the case that the kernel of this homomorphism is not the identity group, and hence G is not simple. So what makes this method work? It works when G has a subgroup of index P or P plus 1. This allows us to get this permutation representation, but more importantly, the way it's set up, you end up getting that any CeLO P subgroup in G is also CeLO P subgroup in K, SK. Or you get a violation of the divisibility criterion. One of the two has to happen. Namely, of course, this is assuming that P has exponent 1 when you factor the order of G as a product of prime powers. When you're in this boat, you have this advantage that you could try to look at these two calculations and try to prove that this happens. SK. That this non-divisibility situation happens and that leads to a contradiction. And why is that useful? Because you're in a situation where the index in SK of this normalizer is easy to calculate because it's just the number of CeLO P subgroups. in SK. And if you're talking about P having exponent 1, a P subgroup has order exactly P. So then the calculation I already had before works. You're just talking about cycles. And so how do you form cycles of length P? Well, you just take P elements in some order. They go together in a cycle, and you divide by P to remind yourself that if you cyclically shift the elements in a cycle, it's still the same cycle. This gives you the number of cycles, P cycles in SK. And then if you divide by P minus 1, that accounts for the fact that any CeLO P group has P minus 1 cycles in it, P cycles in it. And so the result is you get something over here that you can calculate, and if you're lucky, divisibility fails, and then you finally get your contradiction. Alright, so sometimes it's good to work with the alternating group instead of the symmetric group, because this allows you to reduce a power of 2. And in order to do that, you can rely on the following proposition. If you have a subgroup of the symmetric group that has no subgroup of index 2, then it's actually a subgroup of the alternating group. In particular, if you take a CeLO subgroup of the symmetric group for an odd prime, then, well, any subgroup inside it has index of power of P, so it can't be index 2, ergo it is a subgroup of the alternating group, and based on order considerations it has to be a CeLO subgroup, because again 2 is not involved, so it's going to have the same order, and the order of the alternating group is n factorial, k factorial over 2. So it'd be the same power of P dividing both. Now the point of this perspective for applications is the size of the normalizer shrinks by 1/2. So for some counting arguments, you'll find that you need this extra 1/2 in order to get the contradiction to work. So for example, suppose we were looking at groups of order 264, which is 2 cubed times 3 times 11. Let's look at the values n sub 3, well, n sub 2, n sub 3, n sub 11. N sub 2 is going to have to be odds, and it's going to have to divide 3 times 11, so you're going to either have 1, 3, 11, or 33. N sub 3 has got to be congruent to 1 mod 3, and it's going to have to divide 88. So you're going to get 4, 1, 4, 22, or 88 as your possible options. Finally, n sub 11 is going to either be 1 or 12. And so it looks like if we rule out, let's see here. So the smallest k such that n divides k factorial is going to be 11. So we can't have, if we have a simple group of this order, it can't have a group of index smaller than 11. So that rules out 1, 3, 1, 4, and 1. This ends up being the only list that has only one number left. So it looks like it'd be a good idea to have G act on, to assume N11 is 12, and have G act on the CeLO 11 subgroups. And assume G is simple. If we do that, then we have a homomorphism from G to S12. I'll show my work more carefully. I should point out that we've ruled out that these are not options if you're going to have a simple group. I'll take that CeLO 11 subgroup and the index of its normalizer is 12. So it has order 2 cubed times 3, which is 24. No, wait, I'm being silly here. 12. When you divide this by 12, what should you get? 3 goes away. Yeah, you get 22. But what is the index in S12 of 11 of a group of order 11? We already calculated that. It was 110. And oops, you don't have a contradiction here. But if we apply this proposition, we might have some luck. Namely, if G is simple, it has no normal subgroups. In particular, it can't have a subgroup of index 2 because a subgroup of index 2 has to be normal. So we can assume that G is a subgroup of the alternating group under this homomorphism. So I should say phi of G here. And thus I can work with saying that NGP is a subgroup of the normalizer in the alternating group. What is the size of the normalizer in the alternating group? Well, by our lemma, it's 1/2 110, which is 55. And lo and behold, 22 does not divide 55, so we finally arrive at a contradiction. Therefore, we must have a contradiction somewhere. The contradiction is going to have to either be that this homomorphism was not injective, that the kernel was the whole group, or that G is not simple. And either of these two contradictions proves that G is not simple anyway. So therefore, G is not simple. There's no simple group of order 264. So this shows you that sometimes when you're off by a multiple of 2, and that's the only thing keeping you from your contradiction, literally when you're in the case where you have Yeah, it's a very limited use application, but when you're this close and all you need is to divide the right-hand number by 1/2 and still get your contradiction, then all you have to do is work in the alternating group instead. Of course, we still need to prove this proposition, but the proof is not that hard. The first part is trivial. Let's just look at it. We'll prove the contrapositive instead for 1. So assume that you've got a subgroup of the symmetric group. If G is not a subgroup of the alternating group, then it has a subgroup of index 2. That's not too hard. It's called the diamond isomorphism theorem. The diamond isomorphism theorem tells you G intersect AK is normal in G. And it has, you can check that it has to have index 2. Why? Because of course G mod G intersect AK is isomorphic to G AK mod AK, but G times AK is obviously SK, and that's C2. So you have a subgroup of index 2. The only way out is if these two things are equal, and well, if that happens, then G is a subgroup of AK, which is what we're assuming is false. Okay, so let's do part 2. As I already mentioned, if you have a CELO subgroup and P is odd, then it can't have a subgroup of index 2. Therefore, it must be a subgroup of the alternating group. And since the alternating group is order n factorial over 2, if you write SK as a 2 to I really don't care what the power is times its other prime factors, then you'll see that the alternating group has the same prime factors. So in particular, if you take a CELO subgroup for PI, it has order PI to the AI. That's the correct order to be a CELO subgroup in AK. As long as it's a subgroup of AK, which it is by the first part. So then I just have to check this normalizer part. Well, the normalizer part, you just use Frattini's argument. To note that SK is equal to the normalizer in SK of P times AK. Why do we use this? It's mainly to note the fact that since SK, the symmetric group, is not the alternating group, this implies that it is certainly the case that this normalizer is not a subgroup of AK. So it has a subgroup of index 2. Oh, but that's exactly what this normalizer AK is. It is this intersection. By definition, it's those elements that normalize P that are elements in AK, the alternating group. And so since this set has index 2 in the full normalizer, that means exactly half the elements in the full normalizer are even permutations. So exactly half the elements in the normalizer are even. And that's all we needed.